Welcome to Data Science with EJD. In this video, we are still talking about advanced supervised learning, and particularly our focus here is on introduction to neural networks for supervised tasks. Of course, neural networks, um, you know, you get to talk about them under deep learning and all that, but here we are just like trying to touch it a little bit as it relates to supervised learning. So our learning outcomes are expected to be the following. By the end of this module, right, students will be able to define the architecture of a simple feed-forward neural network, describe the role of activation functions, loss functions, optimizers, and training loops in supervised learning. Then implement a neural network using TensorFlow slash Keras. Then train the model on a real-world data set. So here we're using the wine data set, and we can visualize and interpret the training and validation performance. So the theoretical foundations, before I go too far, I think it's always important to show the line numbers where, yeah, like that. So theoretical foundations for this, first of all, we need to understand what a neural network is. A neural network is a collection of interconnected nodes, or what you can call neurons, organized in layers. So the one is an easy way to think about this is the connections, that make up our central nervous system, or you can even look at the brain like that. So when you talk about the brain, you talk about neural circuits. So it's something that mirrors the brain, so to speak. Each neuron applies a weighted sum of its inputs followed by a nonlinear activation function. So, and then we have the idea of a feed-forward neural network, which for instance, a multi-layer perceptron (MLP). So, the structure of a feed-forward neural network is uh, is such that you have an input layer, and then after that you have one or more hidden layers, but then you have the output layer. So you have an input layer, and you have so many layers in between before you now go for the output layer, and each layer is fully connected to the next. All right, so it's a network, as you can imagine. So information flows forward. So it means there are no loops. A loop will be like you have a closed circuit, right? But information keeps progressing. That's what we have as in a feed-forward neural network. So the key components of this, as we will see, are the following. Input layer, like we've just talked about that. So it accepts feature vectors. That's the X now. And then in this data set, we have 13 features. So that's like when you talk about the features, the inputs, right? Then we have the hidden layers. These are intermediate computation layers, and we can use nonlinear activation like ReLU. Then we have the output layer. So this outputs class probabilities using softmax for multi-class classification. Then we have loss function, which measures the error. We use categorical cross entropy for multi-class classification. Then optimizer, which adjusts weights to minimize loss. We use the Adam optimizer. Then we have the evaluation metric for this. Accuracy is used to evaluate performance. So, I mean, we're talking about neural network here, but we see that accuracy is one of the key evaluation metrics for classification algorithms. Now, let's take a quick look at the UCI wine data set. So here we have 178 wine samples with 13 chemical analysis features. And then the target in this case will be classification of wines into three cultivars. And then the goal is to predict wine class from chemical properties. So let's look at the implementation in Keras. So the first thing we want to do is to load and preprocess data sets. So here we normalize the input features for better training performance. That's you normalize so that the data sets can be normally distributed with mean 0 and variance 1. Then you use a one hot encoding for target labels, right? Then you split data set into training and test sets. We can do an 80-20 split or 70-30 depending on what we want. Then we can define the model architecture. So here the input dimension is 13, talking about the features, and the hidden layer 1 can be like 32 units for ReLU, and then hidden layer 2 can be 16 units ReLU. Then the output layer can have be 3 units softmax. Then let's go ahead and compile and train the model. So here we talk about the loss, which is based on categorical cross entropy. The optimizer is Adam. The metric you are looking at is accuracy. Then we have 50 epochs, and the batch size is 8. Um, so the full code, um, of course, because we are using TensorFlow here, the first thing we want to do is to install this. Okay, well, but maybe before I go for this, right? So we talk about the idea of epochs and batch size. Can we see what are epochs? Of course, epochs are like when talking about time, right? It's something close to that. So epochs in neural net. Okay, machine learning for sure. So in machine learning, an epoch represents one complete pass of the entire training data set. So if you pass through the data set one time, that is one epoch. So an epoch represents one complete pass of the entire training data set through a learning algorithm. Essentially, it is a single iteration where the model learns from every data point in a dataset. Multiple epochs allow the model to refine its learning and improve accuracy with each successive pass. So 50 epochs means it means that the model will get through all the data sets 50 different times to give a result. So each time it goes, it gets better on the previous attempt, right? So that's what an epoch is. And then let's talk about batch size. I think that's another idea we saw, the batch size in machine learning. Okay, so in machine learning, batch size refers to the number of training examples used in one iteration. So, number of training examples used in one iteration of model training. So, it determines how many samples are processed together during each update of the model's internal parameters. Batch size influences training speed, stability, and accuracy. So, I thought that was important to clarify. So we've been TensorFlow has been installed. I had installed it before, so that's why it's telling me requirements already satisfied. So if you are doing it for the first time, it might take a bit more time than what it took here. So the next thing, so we see the code itself. So here we need NumPy for numerical calculations. We need Matplotlib for visualization. We need scikit-learn because that's where we're bringing the wine data set from. We need model selection where we get the train test split function. Then sklearn processing where we get our standard scalar to normalize our data. Now TensorFlow, this is where TensorFlow comes in. So we have TensorFlow.keras.models where we import sequential. Then we have TensorFlow.keras.layers where we have inputs and dense, and TensorFlow.keras.utils. That's I think that's where we convert some categorical variables or something like that. So the data set here is we want to load the wine data set, right? So we have, I think I want to do this bit by bit. Let me escape and then create as many cells as possible so we can go step by step. All right. So here we want to, having installed all of that, having done what we needed to do there, so that we import all the data sets and everything. Import all the necessary libraries. So wine is load one. So we say X is wine.data and Y to categorical wine.target. All right. So we run this and it takes some time. So when you see this start, it means it's still running. And then by the time it's done, a number appears there. Okay. It's taking a bit of time. Good. Done now. So after that is done, then we can talk about uh, standardizing inputs, okay, for to make the model work better. So that's where we use our scalar. So we say scalar is standard scalar. So x scaled will now be scalar.fit transform. So we transform the x. Okay, before we even go to that, right? Like I always like to do, I like to see the the data. Yeah, so these are the x values, and then we can also see the y. These are the targets, right? And this is those are the features rather, sorry, and then this y is the target. Okay. Okay, so it's about classification in this case, and then now we can preprocess by standardizing the inputs, so that's done. And then the next thing we want to do is to do the split. We want to split the data set. This is about the most common thing, the most regular thing we get to do for machine learning algorithms. So here you have the x train, comma x test, comma y train, comma y test equals train test split x scaled, whatever you want to scale, you want to split. Now that's the x scaled. Instead of the x itself, so you want to scale it, and then we are doing 80-20 split because that's what the test size is, 0.2, that's 20%. So we can just run this and it's done. Then we now go ahead and talk about the, so we want to define model with input layer. So let me remove this ones. So define model with input layer to avoid warning. Okay, so we don't want some warning coming up. So that's done. And then, so we have model sequential input shape 13 and all that. Then next, we compile the model. So we compile the model, and to compile the model, now you see for neural networks, the steps are more because you are talking about layers of connections, right? So compile model. So you have model.compile, optimizer is Adam, loss is category, cal cross entropy, and the metrics is accuracy in this case. Then you can also train the model. So history is model.fit. Um, so the model you have here already, model.fit x train, y train, and then validation of data x test, y test. 50 epochs, batch size 8, verbose is 1, and then we run that. It takes a bit of time. Uh, you must call compile. Oh, that means I didn't run this. Yeah, we have to call compile right before we can actually get to do this. Now it's fine. So we have 50 epochs. So you see, it goes like that. It keeps going until it gets to the 50th epoch. So it means that the model runs through the data 50 times before we get our final results. So, and then it gives things like accuracy. So, I mean, this data, we are using the one data set. Okay, like you can see the first time the accuracy is 0.33, and then that keeps improving, it keeps going until, so you can see it's getting better and better until we finally have perfection, like it's 100% accurate. So each epoch like that, there's an improvement on the learning process, until we finally, and you also see that the loss keeps decreasing. So at first when we started, the loss is 1.08, and then it decreases to 0.8817. And by the time it's all done, the loss is now 0.0169. So that's the essence of doing this in epochs, right? Or is it epochs we should call that? So having done that now, what we have done there is to train the model. So having trained the model, then we can go ahead and evaluate the model. So we have test loss, test accuracy. So that's model dot evaluate x test, y test, variable 0, print test accuracy. We do this so you can see final accuracy, like we've seen here, is 1.00 already. So that means that the model perfectly classifies the wines as they should be in the right way, right? So the next thing is to now visualize the training performance, where you plot both training and validation loss accuracy curves. Okay, so here, so the figure size, you can define that it has 12 by 5. The loss plots, so here you are doing two plots, history for loss and val loss. So you see all these, you see loss and val loss here. So all these ones now we are plotting them to give us a picture, so we can already see that each of them is decreasing, both the loss and val loss, right? So since you're talking about that's validation loss actually, right? Then for the accuracy plot now, you have accuracy and validation accuracy. Those are the two plots. So if you click on this, you have these beautiful plots now. So these are the loss over epochs, right? So you have training loss and validation loss, and for the accuracy over epochs now, so you have the epochs here. So as the epochs are increasing, the accuracy is also increasing. Whereas as the epoch is increasing, the loss is decreasing. So how do we interpret this? Analysis and interpretation. If training and validation accuracy increase and converge, training is effective. So you can see if training and validation accuracy increase and converge, training is effective. So training accuracy and validation accuracy. So you see both of them, they converge at the end of the day. So that means that the training is actually effective. And a divergence between training and validation accuracy may suggest overfitting. So there's no divergence here, thankfully. So we're good. All right. So then to improve generalization, consider dropouts early stopping or regularization. So the idea of regularization is using things like ridge regression or lasso regression. So optional enhancements, other things we can still do to this. You can add dropout layers between dense layers. We can implement early stopping with callbacks, or we can display confusion matrix or classification reports using scikit-learn, sklearn. So those are some things we can do to this now. Talking about introduction to neural networks for supervised tasks. Right. So with this, we come to the end of this interesting video. Um, so let me know how helpful this has been for you. And if there's something you'd like me to try out, feel very free to let me know. Also, if you have subscribed to the channel, thank you for that. If you have not, please go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Then having done that, don't forget that now we can have membership on the channel. If you want some extra benefits, right, beyond subscription, you can be a member. So just click on join and you see the possible ways in which you can become a member. There are 3 layers right now. It may become 4 later or something, I'm not sure, but you can just explore that. So very importantly, also like and share this video so that more people can have access to the great content I have here. Till I come your way again, keep doing data right. Bye.